Hello and welcome. In this lecture, we're going to cover how we study differences in two population means. In our previous lecture, we discussed how we analyze paired data, which is a special case of this, where we have data on two variables and each observation in the dataset for the first variable is directly linked to one and only one observation in the dataset for the second variable. In this lecture, we're going to talk about finding differences in means in all of the cases where we're not analyzing paired data. So let's get started by looking at an example. The Census Bureau conducts the General Social Survey, which asks people a variety of questions about the demographic categories they fall into, their behaviors and attitudes, and any topics that are of special interest to the Bureau that year. And one of the cool things about the General Social Survey is that many of the core questions in the survey have been asked in the same way since 1972. And when a question is asked the same way every year, that means that the answers to those questions are really well comparable to one another over time, which means that we can study time trends in these variables over decades. So the General Social Survey is a really cool resource. We're going to be looking in particular at an excerpt from the Social Survey in 2010. We're going to be looking at people's level of educational attainment and how many hours per week they work. So the degree variable is a categorical variable that measures what people's highest level of educational attainment is. So all the way from really high educational attainment, like getting a graduate degree, to people's level of educational attainment being lower than a high school degree. And then the hours variable is going to measure how many hours per week this person works. So in these box plots, we're looking at the number of hours per week worked by people in each of these educational attainment categories. So you can see that the median across these categories is really consistent, right around 40 hours per week. So that's a standard work week length for full-time workers. And so the median is really consistent across these categories, but we can see that there is some difference in the spread. So for some of these, you can see the 25% and 75% markers in that box plot are sometimes closer together, sometimes further apart. And there's differences in where the outliers are outside of the whiskers in these box plots. But for the most part, when we look at this, it would be hard to make the case that there's a substantial difference in the number of hours per week that people are working across these different educational attainment categories. So let's say that the main thing that we're interested in is the difference between people who have graduated college and people who have not graduated college in terms of the number of hours per week that they work. So in order to do this, we're going to take our 5 levels of educational attainment and we're going to collapse them or combine them into just 2 categories. So the less than high school and high school degree categories are going to get combined into this new category just called high school and lower. And the junior college, bachelor's degree, and graduate degree categories are going to get combined into this category called college or higher. So we're dichotomizing this variable. We're taking these 5 levels and we are going to split them off into just 2 levels. So let's take a look at what this data looks like now that we've split it into these 2 categories. So we have data on the number of hours worked per week for people who have a high school degree or lower and people who have a college degree or higher, as well as the standard deviations and sample sizes for both of those categories. So for people in the first category with a high school degree or lower, the mean number of hours worked per week is 39.4 in our sample, with a standard deviation of 15.12. And for people with a college degree or higher, the mean number of hours worked per week is 41.8, with a standard deviation of 15.14. And then the sample sizes for each of these is pretty substantial, 667 observations in the first category and 505 observations in the second. We also want to know how these data are distributed in each category, which is what these histograms are going to show us. So the high school or lower histogram looks more or less normal. It doesn't seem to be particularly skewed in one direction or the other. We can see this peak in the middle around 40 hours per week. The college or higher distribution looks a little bit weirder. It isn't conclusively skewed in one direction or another, and it's possible that this is approximately normally distributed, but it doesn't look quite as nice and symmetric as the high school or lower distribution. But we're going to treat it as approximately normal in the rest of this lecture, but that might be something to pay attention to if this is data that you were analyzing in real life. So we want to know if there's a difference between the number of hours worked per week by people with a college degree and people with a high school degree or lower. So we want to have a point estimate as well as a measure of our uncertainty around that point estimate. So a 95% confidence interval is what we're going to construct. So our parameter of interest is the average difference in the number of hours worked per week by all Americans with a college degree and all of those with a high school degree or lower. So the population mean for people with a college degree minus the population mean for people with a high school degree or lower. And our point estimate is going to be drawn from our sample. So the average difference between the number of hours worked per week by our sampled Americans with a college degree and those with a high school degree or lower. In order to use the hypothesis testing approach that we have been using, we need to meet a couple of conditions. So let's go through each of these in turn. The first is, of course, that the observations in each of our groups need to be independent of one another. We can satisfy this by doing two things. First, by making sure that we take a random sample from the population that we're interested in, which we did. This is a random sample. And by making sure that our sample sizes are less than 10% of the population. So in our case, we've sampled a couple hundred people from a population of millions. So that 10% condition is satisfied. We also have a new condition to take into account, which is independence between groups. So we want to make sure that our observations are independent not only within their individual groups, but also across groups. And again, random sampling should take care of that. So since we have a random sample, we're pretty sure that independence between groups is a condition that is satisfied. The other thing that we want to make sure is that we have a sufficiently large sample size that is not extremely skewed. So our sample sizes in both groups are greater than 30, and both of the distributions, when we looked at them, were more or less symmetric. In any case, they weren't extremely skewed. So remember that a confidence interval is our point estimate plus or minus a margin of error. And a margin of error is constructed by multiplying a critical value by the standard error of our point estimate. Now, standard errors vary in how they're calculated depending on the kind of research question that we are asking and the kind of data that we're dealing with. So, in order to find this confidence interval, we're going to specify our point estimate, which is the difference in means across our two groups, so mean 1 minus mean 2. And since our sample sizes are sufficiently large and our distributions are not particularly skewed, they look more or less symmetric, we're going to use the normal distribution, the normal approximation, and use critical values from the z-table. So the only new concept that we need to take into account when doing this test, when constructing this confidence interval, is calculating the standard error for the difference between means. So here's that formula. We're going to take the standard deviation for the first group divided by the sample size for that first group, plus the standard deviation for the second group divided by the sample size for the second group. We're going to take the square root of that entire quantity, and that's going to be our standard error for the difference in means. So let's calculate that standard error using the data from the example that we've been working with. So our two groups are people with a high school degree or lower and people with a college degree or higher. We're going to take the standard deviation for the first group divided by the sample size for the first group, plus the standard deviation for the second group divided by the sample size for the second group, and take the square root of that entire quantity. So you can see how this is worked out. We take the standard deviations squared in the numerators of these terms and the sample sizes in the denominators of those terms, take the square root of the whole quantity, and we end up with the standard error for the difference in means for these groups of 0.89. Now that we've worked out the standard error, we have all of the information that we need to estimate the difference between the number of hours worked per week by people with a college degree or higher and a high school degree or lower, as well as construct a 95% confidence interval around that estimate. So the formula for doing this is to find our point estimate, which is this difference in means, plus or minus the critical value times the standard error that we have. So if you want to, you can take a minute and pause the video and see if you can work this out. So solving this is really straightforward. We're just going to plug in the values that we need in this formula. Our point estimate is 41.8 minus 39.4, and then we have plus or minus the critical value for a 95% confidence interval, which is 1.96, multiplied by our standard error, which we found to be 0.89. So that gives us a point estimate of 2.4 and a margin of error of plus or minus 1.74. So that gives us a 95% confidence interval from 0.66 to 4.14. So we've calculated this 95% confidence interval, but we do need to know how exactly we should interpret that. So I've given you a couple of options here, and you should pause the video and read through them and come up with your answer for the best interpretation of that 95% confidence interval. So the differences between these options are a little bit subtle, but the best and most useful interpretation of this confidence interval is that college graduates work on average 0.66 to 4.14 hours more per week than those with a high school degree or lower. We know that with 95% confidence. So that tells us not just that there's a difference between these groups, but what the lower bound and upper bound are on the size of that difference, and correctly tells us the direction of that difference, that college graduates are on average working more per week than people with a high school degree or lower. So we've been talking about the fundamental question that we're curious about. Let's take a minute to talk about how we would construct the hypotheses that we need to test that difference. So our null hypothesis should be that the mean number of hours worked per week for college graduates is equal to the mean number of hours worked per week by people with a high school degree or lower. So there's no difference in means in the actual population, and any observed difference in our sample is just going to be due to natural sampling variation, not indicative of an actual difference in the population. And our alternative hypothesis is going to be that the mean number of hours worked per week by people with a college degree or higher and a high school degree or lower is not equal. So there is a difference in the average number of hours worked per week across these groups. It really is useful to be able to translate our research question into particular null and alternative hypotheses to test. Another thing to keep in mind is that it's useful when we're talking about the equality or difference between means to go ahead and transform those hypotheses to be about the difference in means. So this null hypothesis that the first mean is equal to the second mean is equivalent to the hypothesis that the mean of the first group minus the mean of the second group is equal to 0. And similarly, for the alternative hypothesis, this hypothesis that the mean for one group is not equal to the mean of the other group is exactly the same as hypothesizing that the mean of one group minus the mean of the other group is not equal to 0. So the reason it's useful to transform these hypotheses is because we want to be able to compare the value that we observe to this distribution under the null hypothesis that has a mean of 0. So we want to see how extreme the value we observe is compared to this distribution under the null. So we transform our hypotheses to be about this particular value of 0. So our point estimate for this difference in means was 2.4, and we calculated a standard error of 0.89. So now what we need to do is calculate a z-score and do our hypothesis test and see whether we can reject the null or fail to reject the null. So because we're using the normal approximation, our process for calculating the z-score is the same as ever. We're going to take our sample quantity minus the quantity under the null hypothesis and divide by our standard error. So in our sample, we're interested in this difference between means. Under the null hypothesis, we've hypothesized that this difference is 0. So we're going to take our point estimate minus 0 is 2.4 in the numerator divided by our standard error, comes out to a test statistic of 2.7. So if we look for this in our z-table, we're going to find a one-tail probability of 0.0035. Since we have a two-tailed hypothesis, we're going to multiply that by 2, and we find a p-value of 0.007. And that is all of the calculation that we need to do for our hypothesis test. So based on the p-value that we found, what is the correct conclusion that we can make from this test? Once again, go ahead and pause the video and read through these possible answers and select the one that you think is the correct one. So we found a p-value of 0.007, which is quite low. And since the p-value is low, that allows us to reject the null hypothesis. That means that it would be very rare to observe the difference in means that we observed if the null hypothesis was true. So the data give us convincing evidence that there is a difference between the average number of hours worked per week by college graduates and those with a high school degree or lower. So based on the 95% confidence interval that we calculated, we have strong evidence that on average, college graduates and people with a higher level of educational attainment than that work more hours per week than people with a high school degree or lower. And that brings us to the end of this lecture on how we find a difference in means and do a hypothesis test about a difference in those means. Thank you for tuning in. I'll see you next time.